Hey, welcome back. This is some good stuff here right now. We're going to look at the periodic table, or PT for short if we get tired of writing it. And basically, it's an arrangement of all the atoms, all the elements arranged approximately by mass, but it turns out actually by atomic number. So it's all the atoms arranged by atomic number, which is Z. And very roughly, right, I'm going to go ahead and try and sketch this out because I mean, I could give you the full periodic table, and I will here in a minute. But I think it's something you should be able to draw. So, for instance, hydrogen is the very first element, atomic number 1, and then there's helium, so that's number 2, and then the third one is lithium, and then beryllium, boron, carbon, nitrogen, oxygen, fluorine is the ninth, and then neon, and then the 11th one is whatever it is, sodium, magnesium, Okay, so they're all arranged by atomic numbers, something looking like that. There's actually a little portion underneath the periodic table, and so I'm going to go ahead and draw a couple of rows underneath the periodic table, and a whole bunch of elements down here, and they actually belong up here. And the real periodic table actually is quite wide, so you have to kind of imagine taking a pair of scissors and making a cut right here and moving these sides apart and then placing this up inside of there. So the real periodic table, if I just sketch it to the top of the screen here, looks ginormous. So boink, and oh my goodness. Okay, you got that big fat row here, and then that middle row here, and then the tippy top, and so on. So this is what it really looks like, right? So you got to imagine a pair of scissors, and we make a snip, cut here, and we move this down, and we move these two sides together, and so that gives us the normal looking periodic table. So this thing down here, right, gets moved down here, and this side is this side, and this part right here is this part right here, and so on. So this is the long form periodic table, which we almost never write. This is the short form, so it is much skinnier, much narrower. Okay, we've lined them all up by atomic number, and what we find is that they form vertical columns where, strangely enough, the elements seem to appear very, very similar. So all the ones in this very first column here, and we're going to call this group 1A, or just group 1 sometimes. All of these are going to have very similar properties. We'll talk about what we call the group here in a minute, and we'll talk about what those properties are. And these ones here, beryllium, magnesium, calcium, and so on, these are group 2A. We're going to skip the middle of the periodic table, and then we're going to have 3A, 4A, 5A, 6A. Okay, I'm going to go dot because I'm lazy, and then 7A, and all the way here at the end, this is group 8A. So these guys here are helium and neon and argon and whatnot. So those are the groups, and the groups go they go vertically. We also have what we call the vertical. Oh gosh, can't keep this straight. The horizontal rows, and we call these periods. So this is the first period here, and then this would be the second, the third period, the fourth, the fifth, the sixth, and I think right now we've got 7 periods on the periodic table, and we call them that because if you imagine sort of lining all the elements up in a row, so for instance, if I write out the first 20 or so elements, and I'll go ahead and just write this out and speed this up, so here we go. I'm just going to go ahead and imagine this is a sheet of paper, so I'm just going to kind of draw the boundary like that, or it's a long inchworm. And so these are the first 20 elements of the periodic table. And what we find is that, for instance, this element here, helium, and this element here, neon, and this element here, argon, all appear very similarly. And so if we count from here, we go 1, 2, 3, 4, 5, 6, 7, 8. And this one, 8 down the road, is just like this one here in many ways. And if we go to this one here and go 1, 2, 3, 4, 5, 6, 7, 8, we get to argon, and argon in many ways is just like neon, in many ways is just like helium. And so we see this kind of repeating pattern. We see it with several of the other elements too. And so lithium, if we go 8 elements down, 1, 2, 3, 4, 5, 6, 7, 8, we get to sodium. And it turns out that sodium is very similar to lithium, and 8 elements down we get potassium, and they're all very similar. So we have what we call this periodic behavior. So just like every 7 days it's Monday morning again, or every 30 days the moon looks about the same in the sky, or every 365 and a bit days the Nile floods again and it's good seed planting season. We have these properties that reappear periodically. So the periodic table sort of arranges those kind of like a typewriter. We start a new line, and these elements line up vertically in groups, and each row, right, is a period. So I'm sorry, I'm very bad at drawing actually. So let me go ahead and pull up a nice proper periodic table from your book, and let's have a chat about it. Okay, this is a much nicer, cooler looking periodic table. So here's group 1A. All these elements like lithium, sodium, potassium, they all have very similar properties. Here's group 2A, so elements like magnesium, calcium, strontium, barium, they all have similar properties. And all the way down the right-hand side, these are these gases: helium, neon, argon, krypton, xenon, radon, and whatnot. And they all have very similar properties. So we can see that elements in the same group seem to behave similarly in these periods, right? So we kind of go through. So there's 1, there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's kind of like a typewriter. We get to the end, carriage return, and we shift on down through. But arranging it this way, the elements line up with very similar properties. And again, we kind of suctioned out, right, this little section here. We kind of cut it out and slithered it and put it underneath. And that's our modern periodic table. So some of these groups have names. So for instance, we can write down group 1A. And group 1A, these are called the alkali metals. Group 2A, these are called the alkaline, very slightly different, earth metals. And most of the other ones have names, but we'll just restrict ourselves to 2 on the other side here. So group 7A, which is right here, and group 8A. 7A, gosh, I wonder if I have enough room here. So 7A are the halogens, and group 8A are the noble, or sometimes the inert gases. So gases make sense. They're all gases. You can fill balloons, and the top couple there will float in the air, and the bottom ones will sink. So there you go. So those are the 4 groups on the periodic table that you need to know. We have some names for these, and the names are written here at the top. The main groups correspond the sections to the very left, the left 2 groups, and the sections to the very right. So these are the main group elements right here, and I'm just going to go ahead and kind of just scribble over top. We have the transition metals. I'm going to go ahead and draw them in green, and these are the funky ones. So it turns out the main group elements behave kind of normally, and but what you find is as you cross the periodic table, it's like normal, normal, crazy, crazy, even crazier, absolutely crazy, and then you transition through this region here, and then you get back to normal behavior. So there's sort of this transition from boring and normal and well predictable and prepared through insane stuff through to normal behavior. And then this section down here, we call this the inner transition metals. Oh my gosh, this isn't marked out on the chart here, so I need to actually write this down. And I'll use black because I haven't used black yet. So these are the inner transition metals because they should be on the very inside of the periodic table. Sometimes they're called the rare earth elements, and you might say, well, gosh, that sounds like they're very rare, and they were thought to be rare at one point, but they're actually relatively common. There's not too many places in the world you can find them, but where you find them in large quantities. And a lot of these elements here, actually, if you have a color TV, the little pixels on the screen that give rise to the colors contain these elements here. So for technology, they're very important. And some of them here we use as contrast agents. If you have an MRI or a CAT scan or something, you incorporate these elements just to kind of make the contrast between different tissues show up much more easily. So they're quite important, it turns out, in this technological world we live in. I guess I should quickly jot down some of the properties. So group 1A, we said, is the alkali metals. And the alkali metals are called this because when they dissolve in water, they form an alkaline solution. So they dissolve in water quite violently, actually. And they form an alkaline or an alkali solution. And what does alkali mean? That basically just means it can neutralize an acid. And I've got a couple little videos that I'm going to try and insert just to kind of show you what we're looking at here. So here is a video that I'm about to press play on, and it is a chunk of sodium that is placed in water. Because the sodium has a lower density than the water, it sits on the top. And let me go ahead and push play, and let's see what happens. you can see it's kind of fizzing around, oh, and then just caught on fire. Isn't that cool? So unfortunately there's no sound, but it floats on the water, it reacts with the water violently, it makes a solution that will neutralize an acid, but it also gives off bubbles of hydrogen, and it got so hot it actually caught on fire there. So that's pretty impressive, huh? If we look at group 2A, those are the alkaline earth metals, and very similar name, I'm afraid. So we often, let's see if I can write this before I can finish talking. We often ask what the name for group 1A and 2A is, and sometimes it's easy to get confused between alkali and alkaline earth. And the earth is just because they tend to be found in mineral form, so a lot of minerals and rocks contain these. So that's why they call them alkaline earth. And alkaline, just like before, when you add them to water, they can dissolve in water. Not so violently, though, but they do form an alkaline solution. So they're often found in minerals or earths. These earths, for many years, were not thought to be possible to separate into anything simpler, but it turns out that you need to pass very large electrical currents through them at very high temperatures, and you can break them down and extract those alkaline earth metals from it. And they do react with water, so just H2O, somewhat vigorously. Maybe that's a good word, so vigorously. So they're not violent, but they certainly do bubble. So let me go ahead and find some calcium here and show you what that looks like. So I've got some calcium in water here, and I haven't pressed play yet, but you can already see that water looks pretty cloudy. Calcium's quite surprising, actually, so a lot of people aren't really sure what to expect, right? It's not like Tums. It is like a sort of a soft, putty-like metal, and when you dissolve it in water, let me press play, you can see there it just kind of rose to the top, and there's lots of little bubbles of hydrogen coming off. And I think someone's putting soap in there, because I don't think those hydrogen bubbles would look like that. But it sort of reacts somewhat vigorously and gets those nice little bubbles. And that solution there, if you were to drink it when all the calcium was reacted, it would neutralize an upset tummy. And so it's a slurry, it's a very chalky solution, but it is pretty good at neutralizing acid. So group 7A are the halogens, and sometimes we use, instead of the Arabic numerals, we use the Roman numerals. So sometimes you'll see it written as VIIA for 7A. And these are so called because they are salt formers. And so these will react with other, typically metals, and form sort of white crystalline things that we call salt. So for instance, I'm going to go ahead and show you a reaction between chlorine and sodium. Actually, it's chlorine gas, which is a diatomic at Cl2, and it actually reacts and forms sodium chloride, which is what we call salt, and there it is balanced. So let me dig that up and show you the video. It's pretty cool. So we got a Florence flask here filled with chlorine. You can see that green gas inside of it. That is the chlorine. And then extending down is a glass rod that's got a little lump of sodium, I believe, in the bottom, and a little bit of water in there just to initiate it. And so if I press play on here, we can see oh my gosh, do you see that? That's pretty impressive, right? See that immediately, that reaction there, chlorine and sodium reacts, and you should see sort of a white cloudy smoke being formed, and that's actually the sodium chloride inside of there. And let me dig up another video too, because the halogens are pretty well known for being great oxidizing agents. They're very good at sort of destroying organic molecules. And let me show you a video of some chlorine with a flour. So this is, oh, don't ask me, I'm a chemist, not a biologist. This is a flour, and it's put into a jar and filled with chlorine gas. And you can do this, actually, maybe I shouldn't tell you how to do it since I'm posting this on the internet, but it's pretty fun and if you ever do it in an outside area where there's lots of ventilation so you don't get chlorine poisoning. But let me go ahead and push play on the right video here. Sorry about that. And you can see that the flour, which started sort of reddy orangey, by the end of the day looks sort of pale white, yellowy, and so it's oxidized the pigments in the petals. So chlorine is very good at doing that. So it's very good at bleaching paper and bleaching flowers and whatnot. And then the last group we have to look at is group 8A. Those are the noble, or sometimes they are called the inert gases. These are exceptionally unreactive, so it is extremely hard to get them to do anything at all. For many years, it was thought to be that they wouldn't react. They were incapable of reacting with anything, but it turns out never say never in chemistry. It is actually possible to get a couple of them to react, if you react them with an extremely violent element, like fluorine, actually, which is an extremely violently reactive halogen. But anyway, let me go ahead and show you a prime use of these. So, for instance, neon is an example of a noble gas, and it doesn't really react, but if you pass electricity through it, you see something really cool. And the atoms glow. So the electrons actually get excited in there, they go to a higher energy level, and when they fall down, they give off that extra energy in the form of light. So this is a neon sign. I thought it was a video, but actually it's the most boring video in the world. It doesn't seem to do anything. But if you've ever seen those signs, they're often filled with not just neon, but they're often filled with argon. So sometimes the green colors are actually argon, and the reddy orangey ones are called neon. They used to, in the business, call this liquid fire. So these things are exceptionally unreactive. You can go to welding supply places and buy argon, and as you do the weld, you spray it with argon. Because it's so unreactive, the weld doesn't react with the oxygen in the air and doesn't corrode or rust before it cools down. So very nice stuff. And those were the 4 groups, 1, 2, 7, and 8, that you need to know for the periodic table. Well done. Thanks for watching, and we will talk in the next video about electron configurations. Bye-bye.